For this problem, we are going to do the electron configuration of 4 different elements, and then we're going to look at the valence shell and do the quantum numbers for each electron in that valence shell. Let's begin with boron. If we look at a periodic table and find boron on the periodic table, we see that we're going to element 5. And if we're going to work our way through from the beginning, we do 1s, 2, 2s2, I'll go ahead and write that down, 1s2, 2s2, and then we come over here to 2p and 1. A refresher, this is level 1, 2, 3, 4, 5, 6. This is the S block, and so we're 1s2, 2s2, and we come over here, this is the P block over here in purple, and so we have 1 electron in that group. So let's write that down. 1s2, 2s2, 2p1. Now the valence shell are all electrons with the highest n. So this is my valence shell, 2s2, 2p1. There are 3 electrons there. So we would need 3 sets of quantum numbers. So where's 1 set, 2 set, 3 sets of quantum numbers. The first number tells me n. The 2 right here is the n, so we have a 2 for each one of those. The S is a subshell, and when S is for an L, or S gives us an L equal to 0, a P gives us an L equal to 1. So for these 2 electrons, they're both in the 0 subshell. They are both in the same orbital. One spins in the positive 1/2 direction and the other one in its opposite direction. Then we go to the next electron, which is in the P subshell, so we put a 1 here. Now I have 3 choices for M sub L. This is the orbital it sits in. We can have, when L equals 1, M sub L can be a -1, 0, or 1. It's important that you know that it can be any one of those 3 numbers that I can put next. I generally go from left to right in my choices, so I put a -1 first, but it is not necessary that you do so. It just needs 1 electron in a p orbital of that P subshell. And it doesn't matter which way it spins, so I'll spin it in a positive 1/2 direction. So that's A. Let's go to B. B is sulfur. So once again, let's look at a periodic table. Let's find sulfur. So we would start up here at the top, and we're going to work our way to sulfur. It would be 1s2. Then we come to here. That's 2s2. Coming across, we enter the 2p block. So that's 2p and count all the way across. We're to 6. Then we enter the 3. That's 3s. There's 2. We struggle across to here, and we have the 3p, and we count over 1, 2, 3, 4. That would be 3p4. So let's write that out. 1s2, 2s2, 2p6, 3s2, 3p4. Now, a quicker way to do that is to look at that periodic table and find the noble gas that comes prior to the sulfur. That would be neon. So we could write neon and say everything of this electron configuration is the same as neon, and then we come across and enter the 3s, put in the 2 electrons, come on across and enter the 3p, and put in the 4 electrons. So another way to write the electron configuration would be neon in square brackets, and then 3s2, 3p4. This is my valence shell. So if I'm going to write the quantum numbers of the valence shell, it's going to be all 4 of these electrons. Let's do the s electrons first. That would be 3, 0 for the subshell, 0 for the orbital. 1 spins in a positive direction, and the other one spins in the negative direction. Okay, one direction, the other direction. So that takes care of these 2 electrons. Now let's go to the electrons in the P. First of all, let's think about where those electrons are located. So I want to draw an orbital diagram for these 4 electrons. We have the 3p subshell with its 3 orbitals. We put the electrons in as follows: 1, 2, 3. We spread them out first, and then we go 4. So when I do the orbital diagrams of these 4 electrons, they are all in the 3rd shell. They're all in a p subshell, but they're in 3 different orbitals. So I'm going to do them in the order that I wrote them down. So I'm going to do this one, then this one, then this one, and then I'm going to come back and do this one. So the first one there. It would be a 3 shell, 1 because it's a p subshell. I'm going to call the first block a -1, and I'm spinning it in the up direction, so I'm going to give it a +1/2. The next one, it's in the 3rd shell. It's still the p subshell, but it's a different orbital. I'm going to call this one 0. It is spinning in the same direction as the first electron I laid down. The next one is in the 3rd shell, the p subshell, but in a different orbital, so I'm going to call it +1. And it's still spinning in the same direction, so +1/2. Coming back to that first, it should match up with this set of quantum numbers. It's 3, it's 1, it's -1, but it's spinning in the opposite direction. So there's the 4 numbers, the 4 sets of quantum numbers for the 3p, with the 2 sets of quantum numbers for the 2s, and that would give you all 6 valence electrons. Okay, let's go to C. C is vanadium. So let's find vanadium on our periodic table. Here it is. Now we're just going to do the shorthand nomenclature for this one because I don't want to go, we're going to do the shorthand electron configuration for this because I don't want to start at 1s and work my way all the way to that. Let's find the noble gas that comes just before vanadium. That would be argon. So the electron configuration of vanadium would be argon. Then we come across and we enter the 4s block. That's 4s2. And then we enter the D block. Now when you count Ds, you start with number 3. So this is 3D, and this is 4D, and this is 5D. So we're in the 3D range, 3D, and we count over to get to vanadium, 1, 2, 3. So we 3D, 3. So 4s2, 3D, 3. Let's write that down. Now the valence shell is everything past the argon. It's the highest N and any inner shell that's incompletely filled, so that would be the 3D. So I have these 5 electrons to consider. For the S, we have the 4th shell, 0 is the subshell. We only have that choice for orbital. 1 is spinning in the +1/2. The other electron is in the same orbital but spinning in the -1/2 direction. So if 2 electrons are in the exact same orbital, they have the same first 3 numbers, but they have to spin in different directions. That's the Pauli exclusion principle. Now for the D, it's going to be helpful for us to think about those 5 orbitals. So I can think about where they're located. This is a 3D subshell, and I only have 3 electrons in there. So these 3 electrons are in different orbitals, but spinning in the same direction. So we have a 3 for the N because of this 3. When you have a D subshell, that is an L of 2. My choices for M sub L are a -2 up to a +2. I can choose any one I want, but I'm going to choose it in order from a -2 up to a +2. I'm going to spin it in one direction or the other. It doesn't matter which one I choose, but generally speaking, when you do an up arrow, you choose the +1/2. The next electron is in the same shell and subshell, but in a different orbital, but spinning in the same direction. The third one is in the same shell and subshell, but a different orbital. Again, I can choose any of the remaining ones, 0, 1, or 2 here, but I've chosen the 0. But it has to spin in the +1/2 direction. These have to be parallel spins. They have to be spinning in the same direction. So those are the 5 electrons of the valence shell of vanadium. The last one we're going to do here is chromium. So let's look at the periodic table and let's get the electron configuration of chromium. Put a little cloud around it here so we can see it. We find the noble gas that comes before chromium, and that's argon. So it's argon. And then we come to across and we work our way to chromium. So we do 4s, 2. In 3D, count over 4, 3D, 4. Now anytime we have a 4 or a 9 sitting right here, we have to consider that there's an exception to the octet rule and that this is not exactly what happens. We're going to promote one of these electrons up to completely half fill that 3D subshell. So that's going to give me instead argon 4s1 3d5. So we've maximized the number of parallel spins by putting in a little bit of energy to promote an electron up to the 3D subshell. It has higher energy, but when that happens and you have that maxed out parallel spins, it actually brings all the energies down and it actually has a little lower energy. So we're going to go back up here. We'll write that electron configuration. It was argon 4s1 3d5. So we know that in this case all your electrons are completely spread out and in different orbitals. So we're going to do the 6 valence electrons for the chromium. The first one that's in the 4s subshell would be a 4, a 0, 0, and spin it. Choose a spin, and I choose +1/2. All other spins will spin in the same direction. So now we're going to the 3D subshell. That's a 3 and a 2, and then I have the choice of a -2, spinning in the positive direction, a -1, spinning in the positive direction, a 0, spinning in the positive direction. What's next? A 1, spinning in the positive direction. And what's last? The last one, got to be in a different orbital. It's in the 2, spinning in the positive 1/2 direction. So what other variations could I have? I could have had every atom spinning in the -1/2 direction. It would still be correct, but otherwise I have no other choice for this one.